Good morning. Today we'll study about the Fermi distribution function. Here, how the electrons are occupied in a energy bands. Here, the electrons obeys the Pauli's exclusive principle. This Fermi distribution function gives how the electrons occupied in a energy levels in a bands. Here clearly explain that it can be proved by in the form of in quantum mechanics. See here? In quantum mechanics, here we have to observe that the behavior of electrons in a energy band gaps. Means here we consider a potential box, one-dimensional potential box, how the electrons will be occupied in each energy levels. It can be given by the Fermi-Dirac statistics, and by using the Pauli's exclusive principle, the electrons will be occupied in a energy levels. We know that no two electrons have the same quantum numbers. So each electron has their discrete energy levels. So this formula, this indicates the Pauli's means the Fermi distribution function, that the f of e is equal to 1 by 1 plus e to the power of e minus ef by kt. Here where the e indicates the energy levels, ef is the Fermi energy level, and k indicates the Boltzmann constant is absolute temperature. This function indicates the Fermi distribution function. Okay. Now, graphically how the electrons will be occupied. From this diagram, see here, from this let us consider n number of electrons. First the electron, this is the energy, the potential box at 0 Kelvin. If one electron drops, first electron drops, it occupies the first energy level, and the second electron if you drop, then it occupies the first energy level. Here what happens? It is a completely filled. The two electrons, one is the positive, one is the means spin up and spin down. Okay? Then it is completely paired. If you drop the third electron, then it comes to the second energy level. The fourth also in second. Then its second energy is completely filled. So on, if you drop the electrons, the energy levels, energy 1, 2, 3 and so on will be occupied. Means each energy level, they have only 2 electrons. Where the 2 electrons are occupied, it is completely filled electron. See here, as more, this is the topmost energy level where all the electrons will be occupied. This topmost energy level is known as the Fermi level. At absolute temperature T is equal to 0, the topmost occupied level is nothing but Fermi level. If other than 0 Kelvin, if you increase the temperature, then what happens? The electrons gain some energy, they will move from one energy level to another energy level. So here, in this case, other than 0 Kelvin, the off-field electron in Fermi level, it is off-field. Means the Fermi distribution function f of e is equal to 1 by 2 at other than 0 Kelvin. Here, the Fermi distribution function f of e is equal to 1. It is equal to 1. Now, see, from this graph, we can clearly explain here. This is the, on x-axis we take energy levels, on y-axis we take Fermi distribution function. Here, up to Fermi at 0, let us consider at 0 Kelvin. At 0 Kelvin up to Fermi level, what happens here? up to Fermi level, all the energy levels are completely filled. Means the Fermi distribution function f of E is equal to 1. So up to Fermi level, all means what happens? The Fermi distribution function is 1 up to Fermi level. See here. And above Fermi level, all the energy levels are empty. Means f of E is equal to 0. So here f of E is equal to 0 above Fermi level at 0 Kelvin. Now, if you move to other than 0 Kelvin, means if you increase the temperature, then what happens? The electrons will be moves from Fermi energy level to any higher level. So here what happens? At Fermi level, f of E is equal to 1 by 2. And here f of E is equal to 1 by 2. Now, from this graph, here we observe that other than 0 Kelvin, we observe at Fermi level it is f of E. The Fermi distribution function is 0.5, means up 1 by 2. And slowly it comes to 0. You can clearly expand. We can slowly, if you move from Fermi level to 1 or 2 energy levels, more than Fermi level, all the energy levels becomes empty. This graph clearly explains the distribution of electrons, in a one-dimensional potential box.